All right, hi y'all. We're gonna do 11.2 today, which is vectors in 3D space. Now that we have ventured into 3D space with plotting points, I started this recording already, but then I stopped because I sounded like a fool. So I am restarting, but I already started these first two examples here, basically to get you caught up. Vectors in 3D space, the way they operate and interact in our computations and things we know about them are the same as they are in 2D space. So in 3D space, if you're adding two vectors, like vector addition, you still just add each of the three components this time instead of just two. So you would take U1 plus V1, U2 plus V2, and then U3 and V3. So this would generate the resultant vector in 3D space by adding each of those three different components together. Multiplying a vector by a scalar in 3D space, just like in 2D space, you just distribute the scalar to each of the three components. Then we have dot product, which again is part of how we figure out the angle between two vectors, same as in 3D space. So if we're doing the dot product of u dot v, we would multiply u1 and v1 together. Sorry, this is a little blurry. My focus is not working great. But this would be u1 times v1 plus u2 times v2 plus u3 times v3. So this would result in some real number. The magnitude of a vector in 3D space, same thing with distance, just like the points in 3D space that we did last class, those are still going to be determined using the same formula. So magnitude of a vector is just basically measuring the head of the vector to the origin, which is just the distance formula with one of your points being the origin. So square root of x squared plus y squared plus z squared for our 3D points. So with a vector, it's just the square root of u1 squared plus u2 squared plus u3 squared. Again, just like we would do square root of x squared plus y squared plus z squared. The opposite vector in 3D space is just changing the direction of the vector. It would be complete opposite from u1, u2, u3. You would just distribute the negative u1, negative u2, negative u3. So that's how you would get a negative or an opposite vector in 3D space. So we'll do a couple of examples here. We've got our two vectors defined for us, u and v. Trying to figure out how to focus this a little better. Oh, well, this is gonna have to do. Okay. U minus v, so that would just be 5 minus 2. I'm not gonna write that step out because I think we can all track that. 5 minus 2 is 3. Negative 1 minus 0, and then 1 minus 4. So there's our vector subtraction, which is really just adding the negative of vector v. Now u plus half of v. So first we would apply this scalar to vector v, then we'll add them to vector u. So we'll have vector u, which is 5, negative 1, 1, and we will add that to half of vector v. So now we're going to distribute the half through here. So it'll be 1, whoops, half of 2, half of 0 is 0, half of 4 is 2, and then we'll add these together. So we've got 5 plus 1, negative 1 plus 0, and 1 plus 2. Then we've got the dot product of u dot v, so we'll have 5 times 2 plus negative 1 times 0 plus 1 times 4. So these two vectors have a dot product of 14. So right away we know those are not orthogonal. So and we'll get to that in a minute, but the orthogonal vectors in 3D space is also determined by having a dot product of 0. Magnitude of vector v, so that's 2, 0, 4. So that'll be the square root of 2 squared, which is 4. 0 squared is 0. 4 squared is 16. So we've got a magnitude of vector v is 20, which is 4 times 5 or 2 root 5. Okay, now to angle between vectors in 3D space. Just like everything else, it is the same formula as angle between vectors in 2D space. So if I've got two vectors, vector v and u, those are in 3D space. The angle between them, we know that the cosine of the angle between them is their dot product divided by the product of their magnitudes. Magnitude of u, magnitude of v. And then likewise, they are orthogonal if and only if u dot v equals 0. So this example here, I'm going to introduce, and then I'm going to ask you guys to pause and try and work through this, and then you can resume the video to check your work if you need to. All right, so we've got a robot arm, and its goal is to move an object from one point in space to another point in space. So these 2 points in 3D space are the 2 points that it's moving the object from to. At which point is the robot's arm more extended? So first, we're going to see the distance from the robot's like shoulder. We'll consider that the origin, the distance from where it would be going from the shoulder to the object in space. So at which point is the robot's arm more extended? We're just measuring the distance from S to O, S to the origin, so SO, and then FO. So we just need to figure out those two distances. Since it's from the origin, it's just the square root of x squared plus y squared plus z squared. So you guys are going to work that out. Part B is asking for the distance between those 2 points. So from S to F. So you're going to calculate that distance in part B. And then through what angle did the arm rotate? You're going to calculate the angle between them. So I'd like you to pause the video, and I'll pause mine, work it out, and then you can check your answer just to make sure you're comfortable with doing these types of operations with 3D space vectors. Oops, that's not what I meant to do. Okay, let me pause my recording. Okay, so hopefully you finished this one up on your own. Let's zoom in a little bit here. So you can check your work here. The distance from S to the origin was 40.91 inches and F was 94.09 inches. So obviously F was going to create the arm extension to be longer than the point S. Part B, what is the distance the robot moved the object? So we're looking for the distance from S to F, which we see, this is the setup here under the square root, and then the end result of 99.08 inches. Through what angle did the arm rotate? It's about 84.7, and you can pause and check your work here if you need to. Okay, moving on, a couple more examples before we learn something new, which will be the cross product of 2 vectors. All right, so here's a couple more applications of the dot product. So here's 2 vectors, v and u. Are they orthogonal? So here we're just checking, just like in 2D space, if 2 vectors are orthogonal, they will have a dot product of 0. So, excuse me, we would just compute u dot v, which would be 3 times 4 plus -1 times -5 plus 2 times 6. So we end up with this result, which is not 0. So no, they are not orthogonal. Not orthogonal. All right, this next one, find P so that this new vector is orthogonal to vector u. So this is a different vector we want to be orthogonal to vector u, which would mean their dot product would need to be 0. So we would just set up the equation applying the dot product. So 3 times 3 plus -1 times p, so negative p plus 2 times -2 or -4. So we would want that to equal 0. We've actually, when we combine like terms, we've got 5 minus p equals 0, which means p would have to equal 5. in order for those two vectors to be orthogonal. Okay, now let me just reiterate that we have only been performing the operation of dot product. There is a second type of product for vectors in 3D space. Now this only applies to 3D vectors. Cross product only applies to 3D vectors. It's not possible to compute cross product of 2D vectors, and you'll see why when I tell you first. I'm going to skip the definition. I'm actually going to tell you what it produces. So unlike the dot product, which produces some real number and helps inform whether or not two vectors are orthogonal, the cross product actually results in a third vector, a new vector. So the cross product of two vectors computes a third vector related to the original two. That is, oops, forgot the word vector. A third vector that is orthogonal to both original vectors. Original vectors. I'm going to try my best to show you visually what this looks like. So again, so the cross product between two vectors takes our two original vectors and results in a third vector that is orthogonal to both. So here's my best attempt at showing that on a video. Here's my two vectors. These can be any two vectors in space. Here, I'm fixing this one here. I'm fixing this one here. So these two vectors, if I take their initial points here and kind of slide them together. So notice I'm not changing magnitude or direction. So their length is fixed because these markers aren't changing size, or these pens, and their direction isn't changing either. I'm just bringing them together so that their initial points are now together, just for this visual. The cross product will result in a third vector. So I'm going to try and hold these together without changing, without changing their direction too much. So if I bring them together and rotate it, so you can see, I can look at these from certain angles where they're in line with each other on a single plane. So the cross product would create a third vector that is orthogonal to both of them. So now you can see this pink one, this new one would be the result of the cross product, and it's perpendicular to both of these. So it's basically perpendicular to the plane created between these two vectors when they're formed together. So cross product takes two vectors in space. This one's stuck, this one's stuck, and it generates a third vector. This is me sticking them together. That is orthogonal to both. Orthogonal to both. Okay, hopefully that helps. Sorry I can't be there to do that in person. So let's go through the actual definition on paper now. Okay. All right, now the formula for cross product is a little involved and just takes practice and repetition. So if we've got our two vectors, u and v, then the cross product that we write u cross v. So you'll hear me say u cross v versus u dot v. To perform this operation, we actually first set up our two vectors in a matrix. So don't panic at the sound of the word matrix. Matrices are not covered in our curriculum anymore for pre-calc. All you have to know is it's a way of visually organizing these like as a set of things. So we just take the elements in vector u, u1, u2, u3, and we line them up as row 1 of our matrix. So it'd be u1, we would just write that value, write this value next to it, write u3 next to it. Then we would put vector v directly below in row 2. So v1, v2, v3. Now to compute the cross product, we're going to be taking products and differences of these elements in a very specific order. To find the first, like I said, the cross product will generate a third vector. So it's going to have an X component, a Y component, and a Z component in terms of that that endpoint, the head of the vector. To get the first component, you're going to cover up the first column here. So then you're just looking at these four. Then what you do is kind of crisscross here. So you would do the product of U2 times V3. So that product of U2 times V3. And then you subtract the cross product, the other cross product. So V2 times U3. And it's okay if your brain is overwhelmed at all of the U's and V's and numbers. We'll walk through some examples and hopefully it'll just solidify everything. So that result of this product, U2 times V3 minus V2 times U3, that result is the first component in the cross product. To find the second component, you cover up the second column. So again, so now we're just looking at, I'm just gonna use a pen here. So we would cover up the second column. That shadow is not helpful. Okay. And then you would have the same process. I would take U1 times V3. So you always start in the top left, take the product with the opposite below. So U1 V3 times V3 and subtract the other cross product V1 times U3. And then the only difference here with this middle one is that result, the middle result, is always negated, just that middle component. The third component, you cover up the third column here, and now we're just working with these four. So now I would do U1, again, start with the top left, U1 times V2, and subtract V1 times U2. So that is the formula to generate a third vector that is orthogonal to both of these, also known as cross product. So again, this gets kind of overwhelming to just look at all the U's and V's. So if we walk through this example, I think that will help very much. So here's U, here's V. We want to find vector W, which is U cross V. So vector W is going to be U cross V. Whichever one you're starting with, in this case, vector U, that's the first row of our matrix. So we would put our three components here, 3, -1, and 2. Vector V is 4, -5, and 6. So this is just the visual to help us set up and apply this formula. So again, to produce, whoops, I kind of have an equals. Go over here. To produce the result, our third vector, vector W, it's going to be covering up the first column to get our first component, and we're going to do the product -1 times 6, which is -6, minus the product of -5 times 2. So minus negative, so we're adding 10. That's our first component. So you can simplify as you go. So we've got 4. That's our first component. The second one, I'm going to cover up the middle column. So I would cover the second column to generate the second entry here. So it's going to be 3 times 6, which is 18, minus 4 times 2. But don't forget that this middle one here is negated. So that result, and then it's negated. So 18 minus 8 is 10, and it's negative. The third component, cover up the third column, same process, 3 times -5, minus 4 times -1, so minus -4, or -15 plus 4. And we have -11. So this right here is the result of the cross product, and the question said it's called vector W. That is cross product. Okay, so if we've generated supposedly this third vector, that is apparently orthogonal to both vector u and vector v, then we should be able to prove that in this next one and actually verify that w is actually orthogonal to the original two vectors. Well, how would we prove that? Same way we did up here in example 3 to check if these two vectors were orthogonal. We just compute dot product. And in this case, since we should be pretty sure that this is in fact orthogonal to both u and v because we just performed cross product. So to confirm that, we need to show that the dot products equal 0. So we want to do w dot u, that should be 0, and w dot v should also be 0. So w dot u, okay, I got to reach around my camera here. So we've got 4 times 3, which is 12, negative 10 times negative 1, so plus 10, and then negative 11 times 2, that's minus 22. So we've got 12 plus 10 minus 22, which is 0. Therefore, w is clearly orthogonal to u. Then we repeat w dot v. So that's going to be 4 times 4, negative 5 times negative 10, and we're adding that. And then 6 times negative 11, which is negative 66. So 16 plus 50, which is 66, minus 66 equals 0. So we've just verified that w is in fact orthogonal to both of our original vectors because their dot product equals 0. So just to clarify, cross product generated this orthogonal vector. Dot product can verify the orthogonality of two vectors. So cross product generates a new vector that's orthogonal. Cross product proves it. Okay, so you guys try this. Find a new vector t orthogonal to both u and v. So I want you guys to pause the video. I'll pause the recording, and then you can come back and make sure you're on track. Okay, I probably could have just left that recording, but now you can check at least the setup. I didn't finish it just because I wanted to make sure you were careful with some of these values. So we've got t, which is going to be the result of the cross product. So again, you should have covered up the first column here and gotten the product of 9 times 3 minus the product is negative 1 times negative 4. So 27 minus positive 4, which results in 23. Then don't forget, and sometimes I just start by doing this for the second entry, putting a negative and a parenthesis out front right away, just to remind myself that whatever I get from the operations in the middle component, I negate it. So covering up the middle column, you would get 0 times 3 minus negative 28. So 0 plus 28, but then you negate it. So it ends up being negative 28. And then the last one, you would end up getting 60 or 0 minus 63. So this is vector t. And that's cross product. That's it. So this is where our chapter ends. And with the rest of class, you should be able to finish your 11.1, 11.2 worksheet.